Exponential growth and decay occurs a lot in business and biological phenomenon and physics applications. Now, you know you're going to have a problem of this nature when you're talking about the rate of change is proportional to y. You'll read this in problems. And what I need you to do is read the rate of change of y is dy dt. Okay? That becomes that part of your problem. Is always equals and proportional to y. Now, k is our proportionality constant and y is of course our variable. Now, if y is a differentiable function of t such that when y is positive and y prime is ky for some constant k, then y equals c e to the kt is a solution to this equation. Now we've already shown you in a previous section that if I have y is c e to the kt, y prime is c times k e to the kt. So plugging this into my equation, c k e to the kt, this is y prime, equals k times y. Okay, this gives us a true statement. So indeed, this is a solution. This is a solution to this differential equation. Now, these are exponential growth and decay models. Now, how would you use them? Suppose I say that the rate of change of y is proportional to y. Right there, you know y prime is equal to ky. Now, not only do you know the differential equation, but you also know the solution. And you know the solution is that y prime, or excuse me, y is equal to c e to the kt, where this k is whatever's multiplying your y. Now, how would we find them? We have two variables, c and k. So let's look at this first initial condition. When t is 0, y equals 2. So I'm going to plug in 2 is equal to c e to the 0, which is just c. So my first initial condition tells me that c is 2. So I'm going to rewrite my differential equation, or my solution, y is 2 e to the kt. Now I had two variables, or I had two unknowns, so I need two initial conditions. So I know when t is 2, y is 4. All right, so I'm going to come over here and plug in 4 is equal to 2e to the k, and here t is 2. So 2 is equal to e to the 2k. Now, in order to solve this, I need to take the natural log of both sides. So the natural log of 2 is equal to 2k. So k is 1/2 the natural log of 2. And you can write this as a natural log of the square root of 2. That's fine. So my solution, oh, I'm not done. It says, what is the value when t is equal to 3? All right. Well, the first thing I need to do is, of course, rewrite my differential equation. Y is equal to 2e. Now, k is, let me put it this way, log of 2 t divided by 2. Let me rewrite that. Didn't do a very good job there. 2e to the log of 2, I'll put the half out here, times t. So what is y when t is 3? Well, all I need to do now is plug in t equals 3. So this is 2e to the 1/2 log of 2 times 3. Now that 3 is outside of there. Now clearly this is not a nice pretty number, but it turns out this is about 5.657. These are calculator problems, obviously. We can also, I'll set this up for radioactive decay. Now in radioactive decay, we tend to talk about half-lives. Now, suppose I have 10 grams of plutonium released during a nuclear accident. What this tells me, this is my first point. When t equals 0, all right, then I have a value of 0 at y equals 0 of 10 grams. How long will it take for the 10 grams to decay to 1 gram? So I want to know the time when y at that time is 1 gram. Now, the half-life of plutonium-239 is 24,100 years. So a lot of times you'll see this written as T1 half is 24,100 years. Now, there are a number of ways to do this. We know half-lives follow the form y equals c e to the kt, and our differential equation is, of course, y prime equals ky. Now, let's look at this. Suppose we want, let's go up here too. Now let's use our initial condition here that when t is 0, y is 10. So 10 is equal to c e to the 0. So c is 10. Now as you can see, c is always going to be your initial amount that you start with. So sometimes you can just read this off your equation. So y is equal to 10 e to the kt. So what is half of our initial amount? Half of 10 is 5. So we know when when the 10 grams reduces to 5, we're at a half-life. So I can say that 5 is equal to 10 e to the k. Now we're at 1 half-life, or 24100. Now this is ugly. So when I solve this for k, I get k is about negative 0.123428761. So our half-life model tells us that y is equal to 10 e to the minus this ugly thing, 0.123428761t. So how long before it takes it to decay to 1 gram? Well, to see how long it takes it to decay to 1 gram, 1 is equal to 10 e to the minus, and I'm just going to put kt here because it's kind of a mess. Solving this for t, this is going to be negative, or no, not negative, excuse me, about 80,059 years.